We're going to be looking at reviewing properties of acids and bases, and just some properties of acids and bases, and then moving on into a procedure called titrations. Okay, so where we're going to use that as a tool in order to find some more information using the acid bases. Okay, all right, so here's a quick review of hopefully what you picked up last year in Science 10. So you're supposed to study acids and bases a little bit and, just mainly look at the difference in properties. So here's a quick summary here. All right, so as usual, we don't just go ahead and eat and drink and taste chemicals in the lab. So so if you were allowed to, so I'm just going to give you some examples of things that you might have at home that you can try if you really want to know what it tastes like, okay? So we have acids. They taste sour, so something that you might have at home is like a lemon, okay? Again, very, very sour if you've tried it. So I wouldn't recommend just drinking some vinegar, but if you just wanted to try a little taste of vinegar, so that, I guess, sensation or what you feel in your mouth is that sour taste, okay? And then with the base, though, if you were to ingest it, a good one, don't try Drano or, okay? A good one that might be like I know this heartburn relief, like Tums and stuff, those ones have a lot of sugar in them, so you won't get that bitter taste. But if you were to just take some baking soda or baking powder and just try a little taste of that, or maybe you've had soap in your mouth when you're in the bath. So those have a bitter taste. So it's a difference from sucking on a lemon. So all right, and then if you were just to stick your hand in these things, right? So again, don't go and do stupid stuff at home, okay? So just like if you wanted to, just with some food, I don't know if you've ever been cutting lemons or peeling an orange and you had a cut on your hand. There's that stinging feeling if it gets in your cut, right? So that's what acids would feel like if you were, for example, to get some really concentrated stuff on you, right? It would start burning and stinging and so forth. An example of what a base would be like, it's more that slippery, soapy feeling. So like an example of something you have at home is soap, right? That slippery feeling. So that's what a lot of bases are like. Okay, from there, reactive properties. Acids react with a lot of things. Big one is that it can, like break apart, degrade metals. Okay, so remember in our single displacement reactions, there was a acid box, and so basically all of those elements in the acid box could come in and displace the hydrogen. So just very, very reactive. Like hydrogen, like if you wanted to look at it from a hydrogen perspective, hydrogen is really low on the activity series table. So so a lot of metals would come in and displace and then create a reaction. So you're going to end up having, a lot of metals, will break apart, okay? All right, and then bases, they try to attack organic materials. So for example, we have base chemicals in things like Drano and sink decloggers, I guess. So because they'll go after any kind of organic material, okay, and dissolve it, like hair. All right, common uses. So like I already talked about stuff that might be around in your house. Lemon vinegar, those are acids, right? Pop has acid in it. Vitamin C is a form of an acid. You can ingest it, I guess, as a vitamin, but anyway, so it is a type of acid. A base, okay, so like a lot of like Tums, Rolaids, things like heartburn relief. There's tablets that you can take, but they do add a lot of sugar, kind of make it minty or fruit flavored, so you can ingest it because it is quite bitter without the extra sugar. So things that you bake with, baking soda, baking powder, soap, and drain cleaner. Okay, from here on, the rest of the table, you were supposed to kind of get familiar with if you use an indicator. So an indicator can analyze just kind of like the pH of a sample, and then present a color to show you kind of what level it's at. So what you were supposed to learn last year with pH is that the lower the pH, the more acidic it was. The higher the pH, so like from a scale of 0 to 14, the higher the pH, it was more basic, okay? And the one in the middle here, sorry, I should move this a little bit. So there, the 7's in the middle, okay? So the 7's in the middle, that's the neutral pH. So if you put it in, I don't know, pure water, you would have a kind of a green color, but then from there, if it's basic, it should be more of the blue tinge, and then if it's acid, it should be more of the yellow. So it slowly goes green to yellow. Okay, so we're looking at maybe the opposite ends here, blue and yellow. That's what you should be seeing. If you have an acid, yellow, uh, blue if it's a base. Okay, so that's the bromthiamyl blue. Okay. All right, phenolphthalein, that's another one that we use a lot. So again, we're using a substance in order to detect the pH so we can kind of determine if something is an acid or base. Okay, so phenolphthalein, that's when we're going to use this here in some labs. So when you do put it into an acid, it just looks colorless. So acids are colorless, transparent, and then you put it in, it still looks colorless. But then if you do the same thing into a base solution, you're going to get a pink, magenta, light purple color to the solution, so depending on how much you dump in. All right, and the last one is litmus paper. So I don't know if you use these two indicators, but the litmus paper, this is an easy one to go to, the little pieces of paper. So there's lots of different colors to these litmus papers, so you can get blue, red, purple ones. But the main thing here is that it will turn, regardless of what color paper that you get, they will turn them all red. So basically, if it was red already, it'll stay red. But if it was blue, it'll go red. If it was purple, it'll go red. Okay. And if it's a base, same thing, the same papers, dip them in. If it was blue, it stays blue, but then the red will go blue, the purple will go blue. Okay, so just look at these ones as like they were half dipped into the solution of base. Okay, so that's a quick summary of what you should have covered last year in grade 10. Okay, so here kind of is the new stuff. I think you may have learned this as well last year. So we have the Arrhenius theory of acids and bases. You're going to learn that this is a limited theory, but there are other ones that are better at explaining things. But we'll start with this one here. It does pretty much a good enough job. So we have acids here. They are you can think of them as substances that will, once you mix them with water, they will break apart and form hydrogen ions, okay? So yeah, that's what we're going to call them with the Arrhenius theory. Later on, you're going to find that you have to actually write the hydronium ion instead. So anyway, so for now, yeah, this is what they do. So here's hydrochloric acid. We're going to look at it as it breaks apart here, and you get the hydrogen and the chlorine ion, okay? Same with nitric acid, sulfuric acid, and carbonic acid. So you're seeing here, these are all 1-to-1, so they consider these to be monoprotic if you wanted to start picking up some of the terminology here. And then just to say that, you get the 1H forming, monoprotic. And why protic? Because they sometimes call the hydrogen ion proton, right? And then from here, this one's diprotic. These are diprotic because, oops, it's forming the two hydrogens, like that. Okay, all right, and then the bases are in this theory as well. They are they produce the hydroxide ion, so that's the OH ion when we're in water here. So you're seeing potassium hydroxide becomes potassium hydroxide, calcium and hydroxide, and then here's ammonium hydroxide. It becomes ammonium ion and hydroxide. Okay. All right. So those are the kind of the definitions of the acids and bases. There are limitations, obviously, to the theory because not everything is a hydroxide-based base, right? So there are other bases out there that, like bicarbonate and so forth, that are bases, but they don't have an OH within them, right? Okay, so yeah, just keep that in mind. You will learn other theories like the Bronson-Lowry theory next year, so we'll just go this far this year. Okay, so from here, I just wanted to quickly do a review of what an acid and what a base is, so you kind of know some of the properties, what colors should appear with the different indicators. And then in general, kind of what's happening at a chemical, just formula standpoint, where the hydrogens are appearing. That's generally what an acid is. If it's OH, hydroxide ion, that's a base. Okay, so that brings us to these double displacement reactions. We kind of touched on them before, but we're going to look at them in more detail. So a neutralization reaction is a double displacement reaction where you have an acid and a base being mixed together and then undergoing a reaction. We've studied ones where they're precipitates before, and it was easy to see that something was forming, and therefore we knew the reaction was happening. With these neutralization reactions, you're going to find that it's all colorless, it's all transparent, and it still looks colorless and transparent when you react them together. So it's very difficult to see using the eye if there's some sort of reaction happening here. Okay, so but what is like? So we're going to look at how we can detect the change and then calculate kind of what the new concentrations are and so forth. But yeah, let's just figure out here what is a neutralization reaction. So we have an acid and base involved, and it's called neutralized because the two acids and bases, right? Like you have a low pH for the acids, a high pH for the base. They will neutralize each other and meet in the middle. So you'll have a neutral substance of water and a salt. So you should have like a pH of 7 in a perfect situation. Okay. So we're going to have a base come in and neutralize an acid. Examples of where you do this in real life is that sometimes your stomach's a little upset, feeling a little acidic, right? They'll say you want to take some antacids like Rolaids or Tums, eat that, and that'll help kind of neutralize the stomach acids. So sometimes when your stomach starts to hurt, it could be just that there's just a little too much acid, so that usually helps. But always could be something else as well. All right, here's an example of a reaction here. So just a typical one. It's hydrochloric acid. That's the acid in your stomach. And this is sodium hydroxide. No, you're not going to drink that. That's kind of like what's in Drano. But anyway, we're taking these two strong acids and reacting them, and it's supposed to form a water and sodium chloride. Okay, so which is just a salt that like you would have on your kitchen table. All right, so that's kind of like the general form. An acid and a base will create water as one product, and then the ionic compound, the salt, for the other one. All right, so if we want to connect our ionic equations here, so if we, again, this is kind of a general balance chemical equation here, but if we look at it from an ionic standpoint, the hydrochloric acid is actually as floating around as hydrogen and chlorine ions. Okay, the sodium hydroxide is the sodium and hydroxide ions. Okay, and then the water is just a pure substance that's going to stay together. It's not going to dissociate. And then we have sodium and chlorine coming out. So see how sodium chlorine, they appear on this side, appear again on this side. They're just spectator ions. So we get rid of them. Here's the net ionic equation. So this is kind of what's the important thing to study here. So we're noticing here when a base and acid are placed together, neutralization happens when you have the same amount in moles, okay, of hydrogen ion and hydroxide ion. So when you have the same amount, when they equal each other, you have reached a neutralization, okay? Obviously, if you kept dumping more base in, because you're trying to neutralize the acid, if you kept dumping more base in, you will go over, and then now it becomes basic. So you start something acidic, and so you start something acidic. Where's my pen here? So you start something acidic, you're dumping a base in, okay? So it's getting less and less acidic, and then at some point you're going to have like where they tie now, they're even. So it's neither acidic or basic. So basically you might have a pH of, I don't know, 2, and you're adding a base that's a pH of 10, and you keep adding it, and at some point the pH scale here, it's going to end up measuring pH of 7. Okay, so that's the middle where it's neutral. It's not acidic or basic. It's in the middle. So so when that happens, you reach neutralization here. Okay, so we're just going to look at strong acids, hydrochloric acid, sodium hydroxide here. And so basically, when you have neutralization happen, you're going to find that the you have the same weights of acid and base in the solution here. Okay. And so you won't have any extra sodium hydroxide left in the solution, because if you do, then you're going to go over the middle mark here, and then you end up becoming more basic like that. So you start acidic, you keep adding the base, and eventually it goes to neutral. Okay, so this is neutral. And then that's neutralization point. But if you kept adding more, then you would end up in the basic region here. Okay, so this way. All right, so we're trying to get it to here and then to stop there and analyze all the properties at that point there. Okay, so here are some other, I guess, pieces of terminology here. So there's something called equivalence point, and there's something called endpoint, okay? So what I want you to do is I want you to look through, kind of look at this like messy example that I made here. So you start with something that was acidic, right? I'm just making up a number like low pH 2, and we're adding the base in, okay? So we're adding this base in here. Okay, so we add this base. So this has a pH that's above 7, so you're adding it in. And so what's happening here is that when you add the base and the acid together, slowly they're neutralizing each other, okay? So what you're going to find is the pH that was 2 is slowly moving towards 7. And it's slowly increasing because you're adding the base. Okay, so then from there, at some point you're going to hit pH 7. You can't see, so we have some tools here, like we can use an indicator. Okay, so like we're going to use phenolphthalein here for our lab. You're going to find that that indicator will not detect the neutral point. Okay, it'll detect when it's more basic. So basically, it'll be colorless, 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 right, all the way through. And even when you hit this point here, it's still colorless. But then one more drop of this base that's added in, one more drop will change the color. Okay, so now it'll become pink, like that. Okay, so once you hit, once it goes pink, you've passed this point here. So this is actually the equivalence point here. Okay. All right. And then, so basically, yeah, it's the point when we're mixing in this whole process and reacting or adding the base to the acid. It's called a titration, and then we're trying to neutralize the acid with the base, and at some point we're going to hit the neutralization, but you won't be able to see that. Okay, it's literally the one drop before it goes pink. So that's the equivalence point, and that means the amount of acid and base that are added, right? They match, and so the hydrogen and the hydroxide ions are equal, right? And then, yeah, so you're going to be able to find that's where the neutralization is. And then you can make some calculations with that. But then when you go one drop over, so one drop over and you stop, that's called endpoint. Okay, so I apologize that this is so messy here. All right, so one drop over, now you're over past the neutral, and now you've gone more basic. So on this side, you're acidic, but over the fence here, you're basic. Okay, and that's called the endpoint. So the point where there is that color that changes, okay? And from there, you can go way over too, but you just want to look at, okay, when it's one drop over, that's the endpoint, okay? So equivalence point, endpoint, they're not the same. Keep that in mind. All right, so right now you're probably just a little bit overwhelmed with all the terminology. Once you start seeing the little examples next, you'll kind of hopefully get more comfortable with what I'm talking about with equivalence and endpoint. Okay, so now that we're gonna reviewed acids and base properties, and we kind of looked at what a neutralization reaction entails. Okay, so you start with some acid, slowly add some base, slowly become neutral, and then you're gonna try to get towards, you're moving towards the basic end of the scale, but then we're looking at when is it right in the middle. Okay, so so knowing kind of what's happening there, there's a technique called titrations that you can use. And so basically, if you are trying to, you can use this technique in order to find something that you don't know. So for example, if you happen to know the base concentration, you know how much base you're adding into the acid, you know how much acid you start with, you can actually figure out the concentration of the acid by running a titration. Okay, so that's kind of where we're moving to now. So you are looking at, you were trying to find the concentration of the acid by adding just the right amount of base, okay, before the color change occurs. Okay, so here we go. I'm just gonna, again, here's a better diagram than the messy one that I had up here. So you're gonna start with an Erlenmeyer flask. You're gonna add a certain volume of acids. You'll know that. And then, so you'll know the volume, okay? but you won't know the concentration of the acid. Okay, so you say for example, this is 25 milliliters. Okay, so we know that. Okay, but we won't know the concentration of the acid. So that's the big question mark. Okay. All right, and then we're on top of like learning about titrations and neutralizations and so forth, we're gonna also learn how to properly use the equipment, okay, for this procedure. So this is a pipette. I'm gonna show you that there's a little bulb or a little apparatus that you can add on the end of the pipette to pull up exactly 25 milliliters if that's what you need. Okay, and then what you do once you find the 25 mils, you're going to put it into the Erlenmeyer flask. And this pipette has been designed so that it actually gives a very accurate 25 milliliters, okay, versus just pouring it into a beaker and then pouring off 25, okay? So this is much more accurate, okay, so the way that's been developed. All right, so from there, like I said, a neutralization reaction, you're going to start off with colorless and transparent solutions. You're going to dump them together, and you're going to still end up with colorless and transparent solutions. So then you need something to be able to show you that things are changing in this reaction. So we're going to add an indicator here. Okay, so we looked at indicators above. Remember, we had the paper test. We have these different solutions here. So what we want to do is we're going to use the phenolphthalein because it stays colorless until it changes. Where here, the rhumb-thionyl blue is all right, but it just it has the different shades of color, so it's a little bit tricky, like trying to find when the neutral point is, because see the greens, I don't know, 6.9, 7.0, it's a slight difference, but it's kind of hard to see the difference, right? So we're going to use the phenolphthalein indicator. So we're going to put that in. I know it looks green, but it'll be colorless. So when you add it, so look here, when you add it to the acid, it'll be colorless. Okay, so we add that in, okay, mix it up. So then from there, you are going to put it with the titration apparatus here. So the Erlenmeyer flask is here. This is called a burette, okay, a burette. And you're going to pour the base into here. So the base goes here. Okay, so what do we know about the base? We know we will know the volume, okay? So this is going to be the, I don't know, the initial reading. And then we will know the concentration of the base as well. Okay, so I don't know, like we can make it up, say 2 mole per liter. Okay, so we know the base, we know the volume because we're going to, this burette basically, you can measure volumes like the initial volume, and then you pour the stuff in, and then you can measure a final volume, and then with that difference you can figure out how much base was actually added. Okay, all right, so from here there's a little stopper here that's a little, you have to turn it to open it and then close it and so forth, and you have to this is the tricky part. You're going to get practice adjusting this part here so that you're not just pouring too much in. You know, you should be able to get to the point where you can control it, so you're adding a drop at a time. Okay. All right. So then from there, so once you set it up, you can start adding, and then you want to swirl this Erlenmeyer flask as well. So you want to take it with one hand, control the little knob with the other hand, and yes, and then be swirling it down here. With some schools, you'll get something like a little stir, like a little magnetic stir, that'll actually spin for you. So it's kind of nice, but we don't have any of those at our school. So you'll have to just kind of do it manually with your hand. Once it drips, give it a swirl. Once it drips, give it a swirl. Try not to touch the burette though, okay? Because we don't want stuff up here. Okay, and there. So what's going to happen is that at the like you're going from, remember, you're going from an acid, you're adding a base in, so that acid is slowly going to neutralize itself. So, right, you can have a pH of 2, and then slowly we're trying to get to that pH of 7. Okay, so as you add the base, you're going to see when the base hits, right, it's going to go pink for a second, but as you're swirling, it disappears. Okay, and then keep going. So at some point when you do hit the neutralization point, right, it'll still be colorless. Okay, so that's why as you're going along, as we feel like you're getting closer to the neutralization point, you'll find that the pink is sticking a little bit longer, but when you swirl, it disappears. You need to, yeah, just kind of keep writing down the volume. Okay, so I got 25.1. All right, add another drop, 25.2. Okay. and you swirl it. Okay, still not staying pink. Add another drop, 25.3. Okay, still not okay, but you add, keep recording it, and then 25.4. Once you add that one, it goes pink, right? It has that little pink and it stays, even though you're swirling it, it stays. So this is the important volume, the one drop before it went pink, okay? So this is where the equivalence point is. Okay, so it's the one drop before it goes pink, and this is the end point. Okay, so we've gone into basic land, because now you've gone over and it's now showing as basic, because the fact that it turned pink, this indicator will be able to tell you if something's basic. If it's not basic, if it's acidic, it stays colorless. At the neutralization, it stays colorless, but as soon as it becomes more on the base end, it'll stay pink. Okay, so that's what you're looking for when you're doing this experiment. You're adding the right amount of base, but literally it's a little tricky here. You have to find the one drop before it goes pink. All right, and that's the volume that's important that you're going to use for your experiment. Okay, all right, so I have a little, what I just said here down here in words as well. Okay, so we're going to have hopefully a day to practice, then we'll run the lab, then we'll write up the lab another day. All right, here's just another picture just that you can reference. So here you have the burette, okay, with the base, titration of sodium hydroxide and sulfuric acid. Yeah. Okay, so and they use bromothymol blue, and that's why it's yellow. And then you got the green. So you can use that indicator as well. It's a little trickier though to find the neutralization point. Okay, so adding so sodium hydroxide's here. Okay, the base is in here. Okay, the acid is down here. Okay, so of the sulfuric acid. Okay, the base is here, and you're adding it. So, okay, with bromothymol blue, you should be yellow to start. Okay, so see how when you add it, you'll see that little bit of green happen here, right? But then you're swirling it, and it'll disappear. Okay, but then the one drop before is the drop that's important, so you have to find that volume. Okay, and then the end point, that's where you've gone over. Okay, so you've one drop over, that's the end point. And then sometimes this happens because at first it is quite tricky to control this valve. So you may need to run a few practice runs before you actually start your lab, okay? So what's gonna happen here is that, if you go way too far over, your results are bad, okay? So if you didn't get that one just before it turned green, and it's now dark purple blue like this, then you've added way too much base here. So it's called an overshot reading, okay? All right, so now that you have hopefully or kind of have an idea of what you're supposed to be doing in the lab, I want to go over just how you go about taking the information that you get from these labs and calculating out kind of what's missing, what's the concentration of the unknown, okay? All right, so here's the first one. Okay, so we have a titration being performed where we have some hydrochloric acid. So pipette is used, so that's that little, okay, it looks like this. Some of them have like a little bulb, so it'll go like, depending on the size of it and so forth. Some of them actually like have a little wider part like this, and then it goes like this, okay? And then, sorry, it should be straight. And then there's a various apparatus, like you might have a bulb, you might have a little, a tool that, draws up the liquid, and then you have to get it to the right mark here. And then, so for example, if it's 25 milliliters, you're going to use this pipette to transfer it to an Erlenmeyer flask. Okay, so you saw the Erlenmeyer flask, this here. This is the glassware that you use for titration. All right, so a few drops of phenolphthalein has been added, and sodium hydroxide is placed in the burette, okay? All right, so so the endpoint was reached. So the concentrated sodium hydroxide, that's the base, was there. You're going to use the readings, the burette readings for the hydrochloric to find the concentration of the hydrochloric acid. Okay, so I just grabbed some actual pictures here. So before we start this question, sorry, I didn't have the burette readings here. So there they are now. Okay. So yeah, there's like, so this was um, the pipette. Sorry, it does have a little balloon part. It's like bigger here, and then it's straight down like this. Okay, and then it usually has a little tip that's angled. Okay, all right, so there's a bulb that you have to use. I used to have to use something like this. It's really tricky to control this, like to pull up the right amount of liquid and then release the right amount of liquid and so forth. Yeah, and then you have to pull the bulb off before you dump the acid into the Erlenmeyer flask, right? So it was a little tricky. We have these now. They're quite neat. They'll actually draw up the acid or the chemical, and then it'll actually lock it in place. So then you can just bring it to the Erlenmeyer flask, and there's a release button to let it out, okay? So anyway, these are the tools that we will be using. Again, you got to make sure you remember that this is glass. You're not squeezing too hard and breaking it and so forth. And here's a burette. There's a close-up of a burette that I wanted to show you here. So here's the valve. It's open right now, but when it goes perpendicular, it closes. So this burette, we've got like it cut in half here, but it starts at 0 at the top, and then it goes down usually like to 50 milliliters, okay? So when I'm taking, when you're running a lab and it says it took some burette measurements, there's going to be a V1 and a V2 measurement. So the V1 is, where you started from. So maybe it's like here, V1 is like 1.65 milliliters. So it's about right there, okay? So you have 1.65 milliliters. Okay, so that's your initial reading. Then you're going to, open the valve, dump the base in. At some point, you're going to hit the end point, and then there's the measurement just before the end point is the 10.35. So let's say, I don't know, it's down here somewhere. That's your V2. Okay, so there's your V1, there's your V2. V1. 6.5. Okay, so that's where these numbers are coming from. If you're just wondering, like, okay, why do you start with a lower volume and then have a higher volume for your final measurement? Okay, it's just because that's the level. It went down. Now, when you find the difference, you'll be able to figure out how much of the base was added. So let's do that now. The difference, and we found now that we use this much of the base. Okay, so let's put all of our known information together. Okay, so right now, what is our scenario here? We know that there's a volume of hydrochloric acid that was carefully measured out with our fancy pipette here, and we know that there are is 25 milliliters, okay? But again, we're going to be dealing with a mole per liter unit for concentration, so let's convert this to liters. Okay, so divided by 1,000, and there you go. Okay, and then we know that we don't have the concentration of hydrochloric acid. That's our goal. All right, so that's that. Okay, so over here, what do we know? We have the sodium hydroxide info. So with our titration and our burette readings here, we found that the volume of the base was, sodium hydroxide was 0.0087 liters. Okay. All right. Then from there, what do we know? Do we know the concentration? Yes, we do. So here, let's go with the highlighting everything here. Highlight, highlight, and then highlight these. Okay. All right, that was given. And then it says, use the burette readings to determine the concentration of the hydrochloric acid solution. So see, we need to find the acid, but we do know the base. Like that, okay? All right, so yeah, we're trying to stick with 3 sig figs here. Add that in. Okay, so now we have our information that we need. So what we're going to do here is do what we've done before. So we need to go get this to moles. Okay, then we can figure out the moles of hydrochloric acid. Okay, and then we can get to the concentration of hydrochloric acid. So kind of, old stuff here, but just applying it to our new little experimental technique here, okay, called titrations. All right, so here we go. So from here, I'm going to use the formula method, and then I'll use the unit analysis method. Okay, so we have, here's the formula method. So we're going to go to moles, use mole ratio, and then back up to concentration here. So we're going to find the moles of sodium hydroxide because we do know the concentration and volume, so we times them together. We get this number of moles. And remember, again, just keep the number in your calculator, don't round up. Then from there, we're going to do a mole ratio, but the nice thing is it's already balanced. It's a 1-to-1 ratio, so some of you might say, I didn't even need to do that step, but just wanted to have it there so you know, wonder, if you don't wonder, so you don't wonder where it went. Okay, from there, and then since we know the moles of hydrochloric acid now, we're going to go find the concentration because we know that we use 25 milliliters, or in this case, 0.025 liters, okay, because we need a mole per liter unit. Okay, so we divide those and we get this concentration, okay, in mole per liter. All right, so there is the formula method. Here's the unit analysis method. I'm taking my known concentration of sodium hydroxide, stacking it, so mole per liter, right, and I'm adding the labels here, okay, so that way you know what number you're using. Then from there, I'm going to use the volume of the sodium hydroxide. So use the stuff that you know and then move towards the one you don't know, okay? So this way I know the liters have to stack up here, okay? The mole ratio is the same, 1-to-1. Okay, so again, if you put the compound in the formula here, you'll know where to stack them, okay? So you'll find that the one that you need to find is always stacked up here. The one that you already have is down here, okay, because they cross out. And then you're moving towards a concentration unit, so it should be mole per liter, so you need to have the liters underneath to divide it out, okay? So when you calculate all of those out, you get the same answer as the formula, people, and we're just going with 3 sig figs here, 3 digits, yeah, to get 0.296 mole per liter, okay? All right, so there is our first titration example. This was a very confident chemist, so that they went through and did one trial. They did this once, okay, and found this result here. But you're going to find that whenever you run an experiment, you always want to run several trials to make sure that you're on the right track, because you may have a really sloppy titration and get a really bad result, which leads to an incorrect calculation for concentration. So here's the next one. This is kind of more like what you're going to do. You're going to run your lab, and you're going to run several trials of your lab, okay? So you're going to find, you're going to have different initial readings and final readings here, getting the different volumes of the base, and then from there, you're always using the same amount or volume of the acid. So from there, we're going to take an average, okay, if these results are good, and I use that number instead of just having like one result, one try, okay? We're going to do 3 tries, and then if they're good tries, they're close together, you're going to average them and then use that number for the volume of the base. Okay, so here's the next example. You're going to add base to the burette, and you're going to measure how much 10 milliliters of acid. So here, let's highlight these. You can add 10 milliliters of acid. Okay, you're going to add, sorry, you won't know the concentration, but you're going to add, use 0.1 mole per liter of sodium hydroxide. Okay, and so there's the volume, there's the concentration. Okay, and then, so yeah, with the burette, you're going to fill it with the base, you're going to run a titration, get this result. Okay, and then what you're going to find is, maybe you started at the top here, but when you used up the solution, maybe it got down to here. So in the next trial, you're going to start from, so here, like you started at 0.1 milliliters, right? And then you ran the first titration and you got to 12.52. Okay, so that's your V2, right? And then when you run another one, you might, keep using the same burette. So then at this point, you got all the way down to 24.98. Okay, and then yeah, and then from there, sometimes you might find that you run out, so then you got to fill the burette and start again, so you end up with new values here. Okay, so the main thing is you're make sure when you're running the titrations that you do have enough. Like once you do the one trial, you'll know, oh, I only needed about 12 milliliters. So I do have enough to do another trial. And if you have a really big burette, so usually they can hold about 50 milliliters. If you feel that you can get another run in, then you can do that. Otherwise, just top it up a little bit before you run the next one, because it's a little annoying to run out and then you have to start again and you get no results. Okay. All right. So yeah, so it's good to always do several trials because, again, this is something that takes practice. And if you are not good at titrating, you're going to be getting results all over the place. So what I'm looking for here is that the difference in volume, the volume of the base that you use, has, an error of like plus or minus 0.1. Okay, so basically if it's off by 0.1, that's okay. But if you're looking at something like off by 0.5, that's too big of a difference. So for example, if you got 12.4 like that, and then the other readings are like 12.9, that's too big of a difference, okay? So I want to see something very close together, okay? All right, so that's good. So the difference, I guess the error, okay, is allowed to be that many milliliters, okay? All right, so from here, what you're going to do is I'm going to take the average of, so we're going to deem these as acceptable observations here. Okay, so and what we're doing here is that we are determining the amount concentration of the acid solution here. Okay, all right, so we'll start with finding the difference, and then I'll do the formula method first. Okay, so I took the average by, again, adding the three. So once, you'll have to do this in the lab as well. When you get your first readings, so like this will be V1, and that'll be V2. Okay, so you subtract them, and then you get to the volume that you use for your base. Okay, so that they call it the titrant. Okay, so from here, here's the average. So again, I'm carrying this in my calculator. It's a repeating decimal series. So, and then from there, since I have that, we're going to go through the steps of mole ratio, and then back up to concentration here. So with the formula method, N equals CV, so concentration times volume. Here's the moles. Okay, again, 6 is repeating. Then the mole ratio, according to the chemical equation, balanced chemical equation here. See, it's a 1-to-2 ratio. So sodium hydroxide is 2, so 2-to-1 ratio here, okay? All right, so if I know sodium hydroxide, I know that sulfuric acid needs to be half of that, okay? Because you're seeing that the 2 is divided over, okay? All right, and then from there, once we have the moles of the acid, we just have to find the concentration by dividing by the volume, okay? And there it is. Okay, so there's formula method and unit analysis. So I stack up the concentration of the base, stack up the volume of the base. So then you'll see that these will cancel out, the volumes will cancel out. Okay, so sorry, like that. And then the moles of sodium hydroxide cancel out, and that leaves the moles of sulfuric acid with the liters of sulfuric acid. So we know we have the right units left. We know we're calculating it correctly. So there is the final acid concentration. Again, all started because you use the titration method in order to find exactly the base that you need in order for that neutralization to occur. And to get to the equivalence point, so then we know what the concentration of acid is at that point. Okay, so I'm gonna the video's probably getting along here, so I'm just gonna end with you should go and try these ones. They're slightly different. Here we have a mass of a solid. It's dissolved in water, so you need to go and find the concentration. And then the solution is titrated with a sodium hydroxide solution of an unknown concentration. So we're kind of going with, we know what's in the Erlenmeyer flask this time, but we don't know what's in the burette, okay? So we do know the volume that's needed in order to neutralize the reaction. And so from there, can you tell me what the concentration of the base is this time, okay? And then here, another example. So again, this is a master titrator, so they just had to titrate once. They found the volume of base that's needed. Here's the sodium, strontium hydroxide was 14.5 milliliters, and it neutralized a 25 milliliter solution of hydrochloric acid. So can you go and find the concentration of the acid? Okay, so just a couple more, and you can check your answers in Brightspace. Okay, so just practice away. Again, I think you should feel pretty confident with kind of what you need to do here. Instead of going to mass, you're going to concentration now. But again, you're collecting some results using a lab in order to find the missing concentration.